Algebra 2, Module 6.1 and 6.3 review. We're going to talk about inverses, composition, exponential functions, and then solving exponential functions. So in the very first problem, we are given the function f of x equals 3x minus 1 and g of x equals x plus 9. We want to find f of g of x. This is a composition of functions. Remember, a composition of functions is evaluating a function with a function. And when you're trying to figure out which equation plugs into which, the second equation always plugs into the first, which means I'm going to take my equation g and replace it with every x in my equation f. So f starts off with 3, then x, which we're going to put in parentheses, x plus 9. Then we still have our minus 1 on the outside. Now we're going to distribute the 3 into the parentheses, so we get 3x plus 27. Then we still have our minus 1. And after combining like terms, we get 3x plus 26, which is our final answer. Second problem, we're given f of x equals 7x squared plus 3, and g of x equals the square root of x plus 9. We again want to find f of g of x. So again, the second equation is plugging into the first. So f starts off with 7, and then we want to square x. So I'm going to take the square root of x plus 9 and put it in parentheses with a squared on the outside. Then we have our plus 3 still. When I square a square root, they cancel, and we're left with 7 times x plus 9 plus 3. Distributing the 7 into the parentheses, we get 7x plus 63 plus 3. So our final answer after combining like terms is 7x plus 66. Number 3, we want to know if the functions f of x equals 2x minus 3 and g of x equals x over 2 plus 3 halves are inverses. And we're going to back up our answer with work. So to determine if two functions are inverses, we want to check that both compositions simplify to x. So first I'm going to start with f of g of x. So we'll have 2, and then in parentheses we're going to put x over 2 plus 3 halves. Then we still have our minus 3. Distributing the 2 into the parentheses, 2 times x over 2 is just x. 2 times 3 halves is 3. Then we still have our minus 3. Combining like terms, we end up with just x. Now this isn't enough to say that they're inverses. We also have to check the composition g of f of x, which starts off with x over 2. So we're going to have 2x minus 3 all over 2 plus 3 halves. I'm going to go ahead and divide my numerator, 2x minus 3, by 2. So 2x divided by 2 is just x, minus, and then 3 over 2 is still 3 halves, and then we have our plus 3 halves. Combining like terms, we're left with x. So because both compositions simplified to x, the answer is yes, they are inverses. Next, we know that the point 5, negative 6 is on the graph of f of x, and we want to know what point would have to lie on the graph of the inverse. So what an inverse does is it switches x and y. So it just makes them change places. It does not change their signs. So when I switch x and y in the point 5, negative 6, we end up with negative 6, 5. So that point has to be on the graph of our inverse. Next, we actually want to find the inverse of our function h of x equals negative 3x minus 6. The very first step in finding any inverse is to rewrite it as y equals. So we have y equals negative 3x minus 6. Next, we want to switch x and y. So we end up with x equals negative 3y minus 6. And now I want to start resolving for y. For my first step, we're going to add 6 to both sides. So we get x plus 6 equals negative 3y. Now to finish getting y by itself, we're going to divide everything by negative 3. So using inverse notation, my inverse, now I don't like to keep the negative in the denominator, so I'm going to move it to the numerator. So it becomes negative x minus 6 all over 3. So the first 5 questions all had to do with section 1. Now in question 6, we're going to take a look at the section 2, where we talked about domain, range, and vertical and horizontal asymptotes of exponential functions. So we have the function f of x equals 4 times 3 to the x minus 2. We want the domain, the range, and any asymptote. So the domain of every single exponential function is always the same, negative infinity to infinity. I can plug in any value for x. There is no restriction on what I can plug in. The range is different. There's only ever going to be a smallest or an absolute largest value that you can reach. And that's based off the number at the end. The number that you add or subtract at the end of your exponential function determines your range. And as long as you don't have a negative in front, in this case we don't, my range, my absolute smallest value is going to be negative 2, and then it's going to continue to infinity. If there had been a negative in front, so it had been negative 4 times 3 to the x minus 2, my range would have been from negative infinity to negative 2. It would have just made that the negative 2 is the biggest value my function can take. Next, we want to talk about any asymptotes. So first, we're going to start with vertical asymptotes. Vertical asymptotes come from any restrictions in the domain. And because there are no restrictions in the domain of any exponential function, there are never any vertical asymptotes. So there are none. So the domain and vertical asymptotes of every single exponential function are always negative infinity to infinity for the domain and none for the vertical asymptotes. For the horizontal asymptote, because that deals with any y values that the exponential function cannot take, that's going to be related to the range. And whatever value you have in the range for your exponential function that's not infinity, that's what the horizontal asymptote is. So because our range contains the value negative 2, my horizontal asymptote is at y equals negative 2. It's extremely important you do write the horizontal asymptote as an equation because it is 1. So you must have that y equals. So domain and vertical asymptote, always the same, they go together. Range and horizontal asymptote, those changed based on the function, and they also are related to each other. So the last section, section 3, we talked about solving exponential equations. Anytime you're solving an exponential equation, you're trying to find the value of x that makes the numbers on each side the same. So in order to do that, the base numbers have to be the same, like they are in number 7. So the very first problem we have is 4 to the x equals 4 to the 3 minus x. Two exponential functions are only ever the same when their exponents are the same. So once the bases are the same, you just set the exponents equal. So we want to find when x equals 3x minus 6. My first step is to subtract 3x from both sides. So we get negative 2x equals negative 6. Then we're going to divide both sides by negative 2, and we get x equals 3. Number 8, we have 64 to the 3x minus 1 equals 16 to the 2x plus 5. Your first step should always try to figure out if you can make the bigger number the same base as the smaller number. So is there a way to rewrite 64 as 16 raised to a power? And there is not, because 16 squared is 256. But there are two different bases we can make them the same. I can either rewrite them both with a base of 2, or I can rewrite them both with a base of 4. And I'm going to go with 4 because that has smaller exponents. So when I'm trying to figure out 4 to what power is 64, I don't want to do 64 divided by 4. I want to plug in values into the exponent of 4 until I get the right answer. So 4 to the first power is 4. 4 squared is 16, but when I do 4 cubed, that's when I get 64. So we're going to have 4 cubed in parentheses, and then we still have our 3x minus 1 in our exponent. Then equals, and I already talked about the fact that 4 squared is 16, and we have 2x plus 5 still. Now that the bases are the same, we can set their exponents are equal. But because I have rewritten the bases, I have to include that number in the parentheses when I set them equal. So we have to do 3 times 3x minus 1 equals 2 times 2x plus 5. Can't forget about that number in the parentheses when we set the exponents equal. We're now going to distribute into the parentheses, so we end up with 9x minus 3 equals 4x plus 10. Next, we want to subtract 4x from both sides. So we get 5x minus 3 equals 10. And we're going to add 3 to both sides. So we get 5x equals 13. Then lastly, divide by 5, and we get x equals 13 over 5. Last problem, we have 1/3 to the x plus 1 equals 81. The first thing we want to do here before getting same base is get them so that they're both whole number bases. We can't have one side have a fractional base and the other have a whole number. So my first step is going to be rewrite 1/3. I can rewrite a fraction with a negative exponent by taking the base number and raising it to the negative 1. So 1/3 is the same thing as 3 to the negative 1. And then we still have our x plus 1 on the outside equals 81. Now I want to see if I can rewrite 81 as 3 raised to a power. So plugging in exponents into my calculator, we get that 3 to the 4th is 81. So now that we have the same base, we want to set the exponents equal. And I have to take into account that negative 1 I have in my exponent on the left, multiply it to x plus 1 first, then it equals 4. Distributing that negative in parentheses, we get negative x minus 1 equals 4. Then we're going to add 1 to both sides to get negative x equals 5. Then divide both sides by negative 1, and we get x equals 5. With any exponential equation, once you've solved for x, you can always plug it back in to make sure you have a true statement. Before you take the Module 6.1 to 6.3 quiz, please make sure you ask me any questions that you may still have and that you have all 3 sections of notes filled out to use on your quiz.